I just have the key on, and what we're looking at is my mass airflow sensor signal. Where I am connected on this is directly to the mass airflow sensor. There is your shot of it. I have the yellow positive lead. I'm using a jumper wire because the Varus leads are short. I'm using the yellow positive leads going to the signal, and black lead known good ground. And again, GM forever has used a yellow signal wire, not the yellow adapter for my scope, but a yellow signal wire forever GM has used. So that's where I'm connected. And what we're looking at on the screen right here is this mass airflow sensor signal. And you guys can see that it is a digital on-off square wave. Drop this time base a little bit, let you see a little bit more of that. But we're looking at a 0 to 5 volt square wave. Let me get this out of the way. This is the smartboard recording program. 0 to 5 volt square wave, and this particular sensor is going to have a variable frequency with RPM changes. This is a little bit outside of our switch input design right now, but I might as well show it to you while we're here. So go ahead and start that. And you see as airflow increased, so did frequency. Unfortunately, this is drive-by-wire, so I can't rev it from out here. So Austin, you want to jump in there for me? Just kind of sitting there for a little bit, if that's okay with you. I know it's a Chevy, you know, Mr. Ford guy. Just a couple of light revs while you're watching that, while we're all watching this frequency. Go ahead. You guys see that frequency changing? Let me drop the time base here so you can maybe see it a little bit better. You know, not exactly a digital square wave, but okay. Let's go up to 100 milliseconds. That really can't see it at all there. It's 20. All right, this would be an example of a signal. Remember when we went through the Varus, when I said to use a graphing meter? I would want to use a graphing meter on this to really look at the signal. What I'm going to do is go back and go to my frequency, and what we're going to do now is graph this frequency. Go ahead and snap it. Go ahead. And you know, we're getting some glitches in here, which I don't like. There's nothing wrong with this, so we definitely have some noise with my long jumper wires, I believe, here. So I threw a little filter in there. And that was really the first time we ever used that filter, huh? So maybe a good example of when to use it. Although, how do you know those glitches are normal or not? I'm telling you they're normal because there's nothing wrong with my truck, and I got these real long jumper wires that are microphones. The other thing, too, is if I would use the sensor ground instead of battery ground, or body ground, that would help. Go ahead, snap that a couple times. And we're at 50,000 hertz. That's too much. Let's go down to 10. Drop this down a little bit more. Go ahead, snap it again. Then what I would do here too is I'd increase my time base to really get a view. Snap it a couple times. So that's what the computer's seeing. You know, a higher frequency equals higher airflow equals add more fuel. Does that make sense? We got a digital signal, we just graphed as a frequency. All right, kill it. Turn the key back on. Nope, changed my mind. Start that back up. Let me show you this another way. We'll go to the scanner. I have the vehicle already identified. And there's another way we can view a mass airflow sensor signal, and that would be the scan tool itself. And what we want to look at is this data PID right here. Oh, nope, that's my grams per second. Let me customize this. That's the conversion of the mass airflow. I'm looking for frequency, it's not here. So I'm going to pick a different data list. We'll go sensor data. Should be in here. There's a whole lot of data lists on this truck, isn't there? And we'll custom this one. There's mass airflow grams per second and mass airflow frequency. It's really the only ones we really need to look at. Then what we can do is graph those and snap it a couple more times. All right, and let's zoom in on our frames. Go ahead, do it again. So the one to the right, what is that? That's the graphed frequency that we just looked at. So this one right here to the right, if we go back to the scope, that is that one right there. So we're looking at what number at idle? This is 3.18. What's that, voltage or is that frequency? It's frequency, and that's in the kHz, so that's 3,113 cycles per second this signal is occurring. Scan tool should tell me the same thing. Where are we at? 3,100 cycles per second. You guys see that? Right there. Top right. I guess I forgot them. You guys can't see my pointer. This would be top right up here. Mass airflow HZ 3,000 cycles per second. You guys understand that the computer is also graphing the signal, that we're really taking a digital signal that doesn't look like that. What does it really look like? It really looks like that. Snap it. Varying frequency signal. We're taking that, we're graphing it. Everybody good? And then scan tool is taking that signal and it's graphing it as well, but then it also, to the left over here, it is taking a value of that signal. In other words, if I were to take an engine coolant temp sensor, it's reading voltage, and then next to the voltage frame on the scan tool, it gives you degree Fahrenheit. Where's that number come from? The engineers wrote that into the program. Said this voltage equals this degree Fahrenheit. Well, in a mass airflow, this frequency, this 3,000 cycles per second, equals 6.81 grams per second of air that's entering the engine. It's a converted value. It's a processed piece of information. Snap that throttle again. You see they both go hand in hand. The one to the left is processed. The one to the right, I would say, is the actual signal. Questions? Okay, shut that off, turn the key back on.
So that's your front door, back door information?
No, good question. So question was the one to the left, the one to the right, is this front door or back door? This is all back door. Okay. On this one, this is all back door. This 4,000 cycles per second, this 4,300 hertz, that's processed because I'm reading this on the right side, I'm reading this through the data link connector, or when I go back to the scope and I read it live, this is the front door tool. This is not processed. And we can make the front look like the back when we graph it. So even on the graphing multimeter, this is still a front door tool. If we want to use Snap-on's terminology, if we graph the frequency, we should see the same number that we're seeing on the scan tool. We should. And what I'm reading now is 0.82, so that'd be 820 hertz. That's not what we were reading on the scanner, is it? Scanner's reading 4,300. I didn't expect to have this opportunity, but with the car not running, basically what this means is the computer's not updating these data parameters. It's not even looking at the mass airflow sensor right now. Why would it? Car's not running. So these PIDs right now are useless. In fact, this is a lesson on bypass testing. I'll come back to this, where if we do a bypass test on this circuit, it's not going to react unless the car is running. Okay, maybe I might be able to show you that, but the issue is I won't be able to touch my T-pin on and off a couple thousand times a second to make a signal. So I don't know if I'll be able to. We'll try it. We'll see what happens. All right, so back to this. Let's say, and I'm going to intentionally cause a problem. So I'm going to unplug my mass airflow sensor, which I just did. And you see that data PID never changed on the scan tool. So proving again that this particular parameter is not even being looked at right now. I go back to my front door or go back to my scope, and we're not going to have a frequency. This is a graphed frequency. We want to get off of this scale. It's not going to help us. What we want to do is go back to our lab scope, volts DC. This is where we would be. And if you have a vehicle like this that has a fixed voltage signal, there's a problem. And we should be able to run it. We'll set a fault code, but that's okay. Can you jump in and start that again for me? All right, we're running in a default mode right now. You see there's no mass airflow signal here at all. All right, shut that off. You can stay there. Yeah, leave the key on. All right. I've been, turn the headlights off. Good. I've been here before, and I've had one of these. And what I want to share with you, I don't know if I'll be able to on this. Let me pause that. And let's try using this at the same time. I'll just draw it here rather than bouncing to my other computer. The reason that mouse is blinking is I'm doing a desktop recording right now, and this is only like a 600 megahertz processor, which is not really intended to do what I'm doing with it. So if this doesn't work, we may have to switch. What I'm doing right now is here's your engine computer, and here's your mass airflow sensor. Sorry for the blinking thing there. Let's say that I get a vehicle in. This is the PCM over here. And I measure my mass airflow signal wire, and I'm reading 0 volts all the time. This is an actual thing that happened to me, okay? So I'm reading 0 on the signal. I know I have no mass airflow sensor signal, and so I proceed to check the mass airflow sensor power, and I proceed to check the mass airflow sensor ground, which actually goes into the computer. It's grounded in the computer. So I check the ground, I check the power, and I check my signal at 0, and I had no signal at all, and I replaced the mass airflow sensor. And I got the new mass airflow and put it in. It didn't fix it. It was my friend's car. It was another instructor here, our brake and suspension teacher. It was a $250 or $450 mistake. Uh-oh, what did I miss? Well, what I didn't realize is on GMs, sorry for this horrible picture, on GMs, the computer sends 5 volts across a fixed resistor to the mass airflow sensor, and the mass airflow sensor pulls the signal to ground to make the 5 volt, 0.5 volt square wave. So in a sense, this is a pull down circuit design. Now you see why we're talking about this. What I should have done before I replaced this mass airflow up here, I should have disconnected the mass airflow. And what should my voltage on this, if I disconnect this down here, what should the voltage read right here? If it reads 5 volts, how's my wiring, how's my computer? Good. Now, I needed, it was 0, by the way, on this truck after replacing the mass airflow and figuring this out. This truck or van had a bad computer, not a bad mass airflow sensor. So do you understand circuit design is important? Do you guys understand that the wiring diagram isn't going to help you here? You just got a wire going between 2 components. So what's the key with this one? We have a known good truck here, right? And we have a sensor that right now is unplugged. This is the type of stuff you should be doing. What do we see on this signal wire? 4.99 volts. Can we call that 5 volts? So how is my wiring from my computer to my mass airflow sensor? If I get a truck in and I have no signal on my mass airflow and it's fixed at 5, how's your signal wire? It's good. So why would a manufacturer flowchart have you check the signal wire for opens and shorts in step 1 of the manufacturer flowchart? Because they do. Why not just unplug it and check for 5 volts? Okay? This is a pull down circuit design. Now, can I take this and make it create a signal? I don't know. Before I do that, let's go back to the scan tool. Sensor's unplugged. Well, let's let you watch it. Start that back up again, just so you can see there's no signal here. Truck's using throttle angle and RPM instead of airflow for calculation. They can get pretty close. Go back to the scan tool, and what you might see potentially, not on this one, I was going to say some of these, they'll still give you a grams per second reading on the left, which is a default number, so you got to be careful with scan data. It'll lie to you sometimes. Go ahead, snap that a couple times. All right, yeah, there's no reaction here at all. I'll have to show you that another time, these default values that a scan tool will give you. All right, can I create a signal? Shut that off, turn the key on. One of the things I know, based on what we saw here before on the scan data, is the computer will not update this data parameter with the car off. Why? Because in this particular case, the mass airflow sensor is not an important sensor with the engine not running. So the computer's eyeballs, if you want to call it, are looking away from this sensor. We're not using it right now. So anything I do on this signal circuit, I'm confident that the computer's not going to change anything because the car's not running. And we saw that we had around 800 hertz live plugged in, but no signal on the scan tool. Actually, the scan tool read 4,000 cycles per second. It was a dead signal, really not changing. What I'm going to do is I'm going to take my, I don't know if this will work, but this would be a bypass test. And I say this in the book that sometimes the bypass test does not work. I'm just going to take this mass airflow sensor signal. I'm going to take this and just ground it. So I have the connector unplugged over here. It's unplugged. I'm just grounding my test light to something metal, hopefully. Kind of limited with what I can do here. And then I'm going to take the test light on and off of this signal wire just like this, okay? And of course the test light's not going to light. But what am I doing? I'm just pulling that circuit to ground, okay? And I'm going to get you focused back on the scan tool. All right, when we do bypass testing, we look for data PID changes. This is what I have listed in the book. So I'll show you. Tell me if you see a data PID change. Nothing, right? It's a little blurry there, isn't it? I want to focus on this guy, not the process signal, but whoops. But this one is really my main focus. We had no signal there at all. Watch it again. Just pulling it to ground with my test light. Nothing. Let's go back to this. Let's go back to the scope. Show it to you there. I'm going to make the signal here. Let me increase my time base so you can see what I'm doing a little bit better. Let's go 200 milliseconds. And take the signal wire and touch it on and off. Okay. That did not work at all. Means I do not have a good ground. So let's try that again, or this test light's bad. All right, so you guys see my makeshift square wave? So I'm creating a signal. Let's go back to the scanner, see if we get a reaction. Scanner, and this would be the mass airflow frequency. This would be the value. And I know it's not going to work. I'm touching it on and off because the computer will not update that data PID unless the car is running. So could we maybe try the test with the car running to see the reaction? I want to try it. It's not going to change anything for me here, but I think it's a good experiment, and I think you guys are getting the idea what I'm talking about. Pull down design, how easy it is to identify wiring problems, and to do a bypass test, which is really cool when you have an issue with a circuit and you want to see the computer react. And that is really a horrible screen. Let's get some other data PIDs in there that are white, just to help this out. Throttle angle, MAP, engine speed. And we'll just keep the mass airflow graph. That maybe should help the focus there a little bit. Okay, start that up. We have no signal. This changed up on us a little bit. My frequency's over here to the left now. My grams per second is over here to the right. And this number to the right, that's a default. What we want to focus on would be this frequency number. Let's see if I can even create a signal fast enough. I don't know if I'll be able to. I'm going to try. There it was. That's cool. I don't want to lose my data here, so if you could turn the key off and right back on real quick. Good job. Good job. That is cool. I didn't think I was going to be able to show you that. What I just did was a bypass test on a mass airflow sensor with my test light. Do you guys understand that I needed an RPM signal for this data PID to update? So the unfortunate part about where we are right now is I could teach you about 5 or 6 different concepts within this same topic. And the hard part about doing it and delivering it to you is which one do I want to focus on. Number 1, pull up, pull down circuitry. Number 2, a digital type circuit and how it relates to the mechanical hydraulic. Number 3, the processed value of airflow grams per second compared to the mass airflow frequency. Number 4, a graphed circuit compared to the actual digital signal. Number 5, some data parameters will not update unless there's a RPM signal. And these are all things we'll be doing the whole class, but within this topic, it's a lot to maybe absorb at one time. Any questions on those? I think I showed it pretty well. Do you guys understand that with the key on this vehicle and that mass airflow plugged in, that I have about an 800 hertz signal that's occurring all the time? I showed it to you when we started. I'll come back to that and show you again, but the scan tool didn't show us that. Why didn't the scan tool show it to us? It showed us 4,000 cycles per second.
Because the computer wasn't monitoring it?
Yeah, we're not monitoring it. Engine's off, so that data PID is useless. You're going to do bypass testing that I want you to learn how to do. You need to understand that sometimes the data will not update unless the car is running or cranking. So your comment might be, well, what if the car doesn't run? Well, my comment back is going to be crank it. If you crank it, will you have an RPM signal? Yes, and then you can do your bypass test. So if you got this car in and you were concerned about the wiring, and you do this bypass test and the computer reacts, how's the wiring? It's good. How's the computer? It's fine. Makes us focus on the sensor. This is extremely useful for pull-up circuit designs that it's normal to have 0 volts with the circuit unplugged. On a pull-down design like what we're dealing with here, I really didn't even need to do the bypass test because we have 5 volts right here on the signal wire measured at the sensor all the time with it unplugged. How's the signal circuit on this design? It's good. The bypass test really wasn't necessary here, but it's cool that I was able to show it to you because this is my mentality, my thought process through a lot of troubleshooting on a car. When you guys come back from break, I want to show you the same thought process on an ignition coil that maybe doesn't have spark. Can we do the same thing? Is the coil bad? Is the wiring bad? Is the module bad? Can we apply the same thought process to this ignition coil? And the answer is yes, and I want to show it to you when you come back.